Alright, this is our lesson 6.07 over the Pythagorean theorem. First, we're going to talk about the square of a number, which, as you may know, is the result of multiplying that number by itself. So, for example, we have this chart here of 1 squared all the way up to 12 squared. So if you want, you could take a screenshot of this particular screen or just make a note of it in your notes from your teacher. That it could be useful as a reference all the way up to integer 12 squared, which is up to 144. And actually, I would say these are typically numbers that people tend to remember also just by memory as well when they go from 1 squared to 12 squared. It can be very helpful when you have those numbers at the ready right away. But again, the principle here is that you're multiplying the number by itself when you're squaring it, right? So if you have this, for example, we have 6 squared, right? That's 6 times 6. Well, we know what that's going to end up being, right? We're going to get 6 times 6, that's 36, right? And then 14 squared, 14 times 14, that's going to be 196. 1 squared, as you know, is 1. 0 squared is actually going to end up being 0, right? Because it's 0 times 0. Anything times 0 is 0. And then 27 times 27, fairly large number, right? That's not one of our numbers on our list. It goes beyond 12, but it's 729. So you can tell me what 35 squared is, right? 35 squared is 35 times 35, and that's going to be 1225, or 1,225. And yes, we encourage you to use a calculator. Now, when you look at the square root of a number, it's a number that, when multiplied by itself, gives the actual number, the opposite of the square. So in other words, you can imagine a square, like just picture a square for a moment here, okay? And take the number 2. Earlier we were looking at 2 squared, right? You can think of that as the area of the square. So the area of the square is 2 squared, which is going to be 2 times 2, which is 4. What you're doing here is you're actually finding the side length of a square. That's what a square root really is. You can kind of think of it like the side length of a square that has that area, right? So if you take the square root of the area of a square, you're getting the side length of that square. That's what a square root really is. So I would take a screenshot perhaps of this particular page as well. It goes all the way up to the integer 15, the square root of 225, so I'd certainly think that would be useful for you to reference. And we can go ahead and try that out on this one right here, the square root of 121. So that one's going to end up being 11. Square root of 64 is 8. Square root of 1 is 1. Square root of 0 is 0, and the square root of 25 is 5. Again, you can use a calculator, or you could have just used that reference page, or that reference slide. So what's the square root of 676? So this one's going to end up being 26. Again, use a calculator if you would like. And now to the meat and potatoes of the lesson. We're going to talk about the Pythagorean theorem. This is perhaps one of the most well-known theorems in all of mathematics. A lot of individuals who go on past their high school education, in past even college education, who might not be in a field related to math, still remember this theorem. And it was proven by, or believed to be proven by, a Greek mathematician by the name of Pythagoras. However, I will point out that it was used long before the Greeks were discussing it. The Egyptians understood the concept of the Pythagorean theorem when they were building the Great Pyramids, among other things. So the Pythagorean theorem has been intuitively understood for millennia, and its main purpose is that it relates the lengths of the sides of a right triangle. What was it used for? A lot of times it was really just used to determine lengths, specifically that had some type of right triangulation. So it can be used to solve for unknown lengths as long as we know 2 side lengths of that right triangle. And so here we have an image of the right triangle, and what we want to point out is that this theorem works for all right triangles, and it's described above. The sum of the squares of the legs of the right triangle, A and B, is equal to the square of the length of the hypotenuse. So when you're looking at this right triangle right here, the legs of the right triangle are always the segments that are perpendicular to each other. That's why they're the legs, right? So those are the legs of the right triangle, and the hypotenuse is opposite, right? Hypotenuse is always opposite. It's always opposite the right angle. Right, so you can see the right angle there with the classic little square box there. And remember, it's the longest side in any right triangle. It's the longest side. So we have a squared plus b squared equals c squared, or more appropriately, leg squared plus leg squared equals hypotenuse squared. So looking at an example, we are told that A is 6 and B is 7. So we have a leg here and a leg here, and we're looking for C. So we can use Pythagorean theorem, 6 squared plus 7 squared equals C squared. So that's 36, right? We're squaring 6 and 7, so maybe use that reference sheet that we gave you, or that reference slide that you took a screenshot of, and you're adding those together. So when we add those together, we end up with 85 equal to c squared. Now the question is, how do we get rid of c squared? We don't want c, we want c squared. So what we can do is we can take the square root of both sides. Right? Remember how you get rid of the area, right? This is the area. We have a square with side length CC, so you get c squared. How do you get the side length to c? Well, you take the square root of both sides. Now when you take the square root of both sides, we want to be a little careful here, because we understand that this number 85, when you take the square root of 85, you're going to end up with something that goes on and on and on, and we really want to approximate it, right? So if I just go out here and say, oh, that's equal, well, it goes 9.21954 ... It keeps going on and on forever, and eventually we have to approximate it. So that's why when we want to round, let's go ahead and round to, let's say, 1 or 2 decimal places. Now, that's called the tenths place or the hundredths place. So for me, I'm going to go ahead and round to the hundredths place. So that's 9.22, and look at, I'm using the approximation symbol here, right? So if you don't know that, remember that means approximation right there. This symbol right here. Okay? So we're approximating our answer. So now we have the approximate value for C is about 9.22. The exact answer is the square root of 85. So you can try this one for yourself. You want to solve this Pythagorean theorem here with 6 and 8 instead, and see what you come up with. You should have selected 10. You have 2 legs, 6 squared and 8 squared, and they're using x in place of c, which is totally fine. So here we have 36 plus 64 equal to x squared, which is equal to 100. And you have to take the square root of both sides to get rid of x squared. So the square root of 100 actually is exactly 10. So we have an exact answer for our hypotenuse in this case. Now you use that to find the hypotenuse. Those are examples of finding the hypotenuse. Now we're going to look at solving for a triangle leg. In other words, we're going to be missing a triangle leg, a right triangle leg. So the things that we want to point out that are important for you to keep in mind is that it has to be a right triangle, and we're going to use the Pythagorean theorem and set it up like we're always supposed to. However, we have to potentially move numbers around to get that variable by itself, to get that leg by itself. So let's go ahead and take a look at an example of that. So what is the value of b when a is 9 and c is 15? So what we know is we have 9 squared plus b squared is equal to 15 squared. So here I can go ahead and evaluate 9 squared as 81. My variable I've identified as b squared, so this whole time this is the variable they're referring to, the leg squared. 15 squared is 225. And so here what I would do is I would subtract 81 on both sides. Okay, so I'm subtracting 81 on both sides. You want to break it up like that and make it organized, that's fine, you don't have to. Then b squared is going to equal 144. Now I can take the square root of both sides to get the leg b by itself, and b is going to equal 12. So I know the missing leg is supposed to be 12. Okay, this is what we were referring to when we had to solve for a missing leg. This is exactly what we want to do. So I want you guys to try this for yourself in this problem. So here we have 7 for b and c is 25. So we have a squared plus 7 squared is equal to 25 squared. A squared plus 49 is equal to 220, or not 225, 625. That's 25 squared, not 15 squared. And we're going to now subtract 49 on both sides. So this gets me a squared is equal to, and we'll go ahead and separate this out because we want to be consistent, 576. So then if we have a squared equals 576, we'll take the square root of both sides and we get a is equal to 24. Okay, so a is going to be 24. That's going to be our answer here. Okay, you have your schedule, of course. This reminder that will be your benchmark testing as well for your middle of year assessment. And we have our exit ticket here. You have to determine the hypotenuse in the first example. So you're missing the hypotenuse, so refer back to those first few examples of Pythagorean theorem. Here you're missing one of the legs, however, so you have to refer to those last few examples that we were working on in calculating. So in other words, remember how when we were missing the hypotenuse, we had to add the sum of the square, or they had to determine the sum of the squares of the legs of the right triangle to find the hypotenuse and take the square root, of course, as opposed to we had to do some subtraction with our second example here. And again, there's examples in the notes that you can refer back to that demonstrate both of those. Now this one says, what is the value of x in that right triangle? So what I want you to think about is that both angles are 45 degrees. What does that tell you if both angles are 45 degrees? What should that tell you about the value of your variable? That should give you a pretty good hint or pretty good idea for your exit ticket. And so this is going to be our lesson for 6.07 over the Pythagorean theorem.